jury duty. Okay, so then you have to make special arrangements with me, so you can do it either before or right after, you know, some point, right? So yeah.
Yeah.
All right, interesting question. I don't have all the answers right now, but let's figure that out. Okay. All right, so I'm going to start with this, which seems like a little odd, but I hopefully can convince you this is a great way to segue into what we're going to talk about today. So here is a very simple system. On one hand, there's a little shaker. There's a rope that basically hangs off a pulley. And so when I shake this thing, I will get the rope to kind of like go back and forth, okay? And so if I make the frequency of the shaking correct, I can create something like this. This is just a standing wave, okay? So this is a rope, it goes up and down, and it forms a so-called standing wave. I think we are familiar with this, but it's an interesting thing, okay? Because what you will see here is that at this point, the amplitude is 0. At the end, here, is also 0. And then there's a couple of positions there where the amplitude of that rope going up and down is 0. Okay, so this is a great analogy with our electron wave, in a way, because we found last time that the electron wave has to fit in a box, but at the end, it has to kind of go to 0. The amplitude of the wave has to go to 0. Same here. Right? At the end of the box of course stops here, starts there, or vice versa. It's the same kind of scenario. Another kind of interesting consideration is if the electron is a wave, and it looks something like this, then the question is, where is the electron at? Okay? Well, if you look at this picture, and you say, well, this rope makes the wave, and I ask you, where is the wave? Well, the wave is that whole thing, right? So when I ask you, where is the electron at? The electron is basically this, okay? It's everywhere, and the chance to actually see it most likely is at the locations where the amplitude is the highest. So it is a probability distribution of finding the electron in particular locations, very high probability, in other locations, very low probability. At these points, if this would be the electron, you will never find the electron because the amplitude is 0. Therefore, the wave function squared is 0. No chance of finding the electron. Okay? So the thing is that if we assume that the electron is described by a wave function, we have to kind of let go of the idea that we're thinking purely about a little point in space that is definitely somewhere. We have to let go of that because we have to now think about it as a probability distribution that looks like a wave. That is what the electron actually is at that point. So if you play guitar, you may have seen this picture before. It's the same thing, of course, with that kind of like shaking guitar string. It has certain nulls and places where the amplitude is maximum when you kind of like strike it, right? And there's different kind of tones that you can make because you can have this oscillation taking place in a variety of ways. All of these waves that you see here have the same condition that at the edges it disappears to 0, and the only difference is that you add every time half a wave more. Okay? That's the same thing as we kind of did last time with the electron. Every time we add half a wave more, we can fit another solution into the box. Same here. You can fit another tone into your guitar. Now let's move from this kind of one-dimensional, very much idealized picture to 2 dimensions, because you can have waves in 2 dimensions. Okay? Let's stick with the guitar theme. Why not? Here's the guitar. This is the soundboard of the guitar, and I can visualize the amplitude of how that board actually moves. by pouring sand on it. You can try it. Put very fine sand and then kind of kick it, and then it actually makes certain oscillations. And here are like 3 different tones that the soundboard is making. And you see in all of these cases, this looks like a 2-dimensional standing wave. Okay, so a 2-dimensional standing wave. The same picture as before, but now not in 1, but in 2 dimensions. You can have a standing wave in 2 dimensions as well. Okay, but let's move now to our world, the world of atoms and molecules, and look at these beautiful pictures, okay, where we have people with very fine instrumentation that are able to put atoms in particular locations. And what they've done, they've taken a surface, this is a metal surface, and they make a certain shape of individual atoms that they put in a kind of like a fence that they create, okay? So on the top, you see this very nice hexagon, circle, triangle, and here a square, where every little point here, this little pointy thing, is an individual atom that sits on the surface, okay? That's not really what I want to talk about. I want to talk about what happens inside the region that you create by building this little atomic fence, okay? Because as you can see inside, you see very interesting patterns. What is that? Well, it turns out that at the surface of the metal, there are electrons that are kind of quasi-free to move around. It's the surface electrons, okay? But if they hit the barrier, the fence, then they can't go beyond that. So they're kind of captured in this little space. And what happens is that in this little tiny place, you get this wave-like shapes. The nicest one is basically the one on the right top, where it looks like a pond with a little kind of wavy pattern in it. Those are basically the electrons on the surface that are now confined in 2 dimensions. Okay, they're confined in 2 dimensions. They are waves, and therefore they make these wave patterns, standing waves with particular wave patterns that fit in these 2-dimensional boxes. There are locations where the wave is high, and there are locations where the wave is very low. What does that mean? Same thing. Wherever the amplitude is high, that's where you are likely to find the electron when you do a measurement. And then there's locations where you will not find it. That's like where the wave is depressed. Okay, and this was how the measurement was done. Take a very sharp point, an atomic tip, and measure where you get so-called electron tunneling. And when you get electron tunneling that's the highest, that's most likely where the electron sits on the surface. In locations where the electron is not, you don't get a tunneling current, and that means the signal is lower. So it's exactly measuring where you can find the electrons. The beauty of these pictures is that you can see the electron wave. Literally, you can see the electron wave. If the electron wouldn't have wave-like properties, you would not see this. Okay? So if de Broglie was not correct by saying that small particles can have wave-like behavior, then this would not show up. But it does. And that's why we have to contend with it. Okay, so let's take this 2-dimensional scenario and see if we can mathematically describe that. Last time, Monday, not too long ago, we considered only 1 dimension and we found solutions. Sine waves. Okay? We also found energies that are associated with each of these states, each of these wave functions. The wave functions, there were a whole bunch of them, and we labeled them by n. N started at 1, went to infinity. That means we also have, for each of these psi n states, we have an associated energy of that state. So let's look now at 2 dimensions. I'm going to make the problem somewhat manageable by assuming that my box now is a 2-dimensional box, very much like the last time. That is a square box. That's the easiest thing I can deal with at this point. So, what does the Hamiltonian look like for the square box? The same as before. Inside the box, the potential energy is 0. I only have kinetic energy. But I have 2 coordinates, x and y. That's why in the Hamiltonian, I have now 2 derivatives, 2 second-order derivatives, one along x and and one along y. I can simply add them up because x and y are orthogonal to one another. That means they have nothing to do. There's no cross terms between x and y. They're completely independent. I can just independently add them in this nice square box arrangement. Okay, so here's the box. Last time we had a line, now we have a box. That's two-dimensional. I have lengths along x. I have a length of the box along y. And then inside the box, there is no potential energy, meaning V equals 0, just as before, for the one-dimensional case. Outside of this box, there is also potential energy, which is infinity, just like last time, but now expanded in a two-dimensional picture. Question, how do I solve this problem? Or is it solvable at all? The answer is, actually, it's quite similar to the last situation. Okay, so what I have to do, I have to solve the time-independent Schrodinger equation, try to find the wave functions that are eigenfunctions of this new Hamiltonian inside the box. Now what I will find is that this wave function is now dependent on two quantum numbers, one along x and one along y. They are independent because x and y are orthogonal. They have nothing to do with one another. So I get two n's. One is called nx, and the other I call ny. Okay, and that's why the energy now has two labels, nx and ny. There's now two quantum numbers. I have two dimensions. I have two quantum numbers. This turns out to be something rather general. Since an atom has three dimensions, we expect three quantum numbers. Okay, and they are, and we'll get to it later, but I can of course tell you, and you know already, that those are n, we have L, and we have ML. Okay, those are the three quantum numbers. We'll get to them and what they mean, but that's the basic kind of rule that we'll follow here. Okay, two dimensions, I get two quantum numbers. Three dimensions, I need to have three quantum numbers at least to describe my three-dimensional wave. Okay, so I'm going to tell you exactly what the solution is. The solution is surprisingly simple. You can prove it to yourself. It's very easy to prove that this is the right solution. I'm going to take the same sine waves from last time. I'm simply going to say I have a sine wave along x and I have a sine wave along y. And the total solution is simply the product of the two. All right? So the total wave function is a function of x and y, but it is composed of two functions, where one function runs along x and the other function runs along y. Little psi x and little psi y, and they have exactly the same shape as those one-dimensional solutions. Okay, so I can write it in this way. Two sine waves, but in the argument I have now for x, nx, Lx in a denominator, and for the y part I have ny and Ly in a denominator. Okay, so I simply multiply the solutions for x and y together. In the front I get prefactors. Okay, I don't care what they are at this point. You can figure that out. You can normalize this whole thing if you want. But there's a contribution from x and a contribution from y. So the general form of this two-dimensional solution in this two-dimensional box looks like this. Now, the energies that these wave functions have look like this. I have two quantum numbers now. Okay, so each wave function is defined by two quantum numbers. I call them nx and ny. Each quantum number, solution, each wave function has now its own energy, and the energy is the energy that I will be getting along x, and the energy I'll be getting along y. Just the sum of the two. It's very, very easy to prove that if you put the form of this wave function in the Schrodinger equation, that the total energy is simply the sum of the x contribution and the y contribution. Each one have their own quantum number. Okay, so if I write that out, I can write it out in the following way. The x contribution is this, the whole thing. So h squared, n squared, 8ml squared. That is the same shape, the same form of the energy that we had last time. But I also have a contribution from y, and therefore I'm going to add the y part to it, okay, which is here. In this way of writing, I simply extracted the constants h, 8, and m, because those are the same for both x and y. So this is a very convenient way of writing the energy of a given two-dimensional state, two-dimensional wave function in a two-dimensional box. Okay, so let's look at these two quantum numbers, because that's a little different from before. Previously we had only one, now we have two. So let's just fill out these quantum numbers, just some random choices, and see what we get, and calculate the energy. Let's see what we get if I choose nx to be 3, that's a valid solution, and ny to be 1. Okay, so in that case, actually one more assumption that I'm having just to make my life a little easier, I assume that the box is square, meaning Lx equals Ly, which I simply call L. Okay, so the length along x and y are the same. Okay, so what is the wave function? Some sort of pre-constants, and then the sine function contributed along x, the sine function contributed along y, so that's the shape of the wave function. That's what it looks like. I'm also giving it labels now. I'm going to call this wave function psi 3, 1, meaning nx equals 3, ny equals 1. This is the shape of the wave function. What is the energy? The energy is a bunch of prefactors, where L now is the same for each, so L becomes also part of this prefactor. And then I have just n squared plus y squared. Nx squared plus ny squared, which is 3 squared, because that's nx, plus 1 squared, that is ny. And so what I'm getting between parentheses is 3 squared is 9, plus 1 is 10. So the energy of this state is this, 10 times h squared divided by 8ml squared. I'm going to call it energy 3, 1, because that's the energy of the 3, 1 state. Okay? So the energy of this wave function is that number. Okay, fairly well. Let's take another scenario. Now I'm going to say nx equals 1 and ny equals 3. Okay, so I'm going to switch. Of course, the box is still the same, so a square box. What is the form of this wave function? Is it the same? Well, it's not exactly the same, okay, because the roles of x and y have reversed. Okay, so I get the prefactors, which are now swapped. Along x, I have the 3 is gone now because nx equals 1, so I get pi x over L in the argument of the sign. And for the y part, I get now the 3 in there, right? So I'll get 3 pi y over L. So if you look at these two wave functions, they have clearly some similarity, but they're not the same. And they are not the same because they are two different states. The two different states, the two different solutions of the Hamiltonian, they are independent of one another. They are orthogonal because they're part of an orthonormal set, if you normalize the functions. These two functions are part of a complete set, and therefore they must be mutually independent of one another, and they are not the same. You can show, I will not force you to do that, but if you take the overlap integral of each and you integrate over the entire box, the answer is going to be 0. There's no overlap between these two functions because they are mutually orthogonal. They have different labels now, but that is psi 3, 1, the one below it, psi 1, 3. Clearly, two different states. Two different states in which the electron can sit. And they are orthogonal to one another. What is the energy of E1, 3? Do the same computation. And so what I'm getting is 1 squared plus 3 squared equals, hey, that's the same. Okay? 10h squared, 8ml squared is the same solution I got up there. That is interesting. So, I'm getting, I have two wave functions here that I considered. They are independent solutions, so they have nothing to do with one another, necessarily. They're not coupled or anything. Independent solutions, yet they have the same energy. Is that a problem? No, not a problem. Why should that be a problem? There's nothing that says you cannot have two wave functions that happen to have the same energy. That's okay. All right? And there's a word for that. If you have two solutions of the Schrödinger equation for the same system, and they have exactly the same energy, and these two wave functions or more, you can have more of course, are called degenerate wave functions. They are degenerate with respect to one another. The word degenerate is a weird word, but in our context it simply means that they have the same energy. That's what it says. Okay, so if you see degenerate wave functions written down in the quantum mechanics book or in the chemistry book, then you know that means these wave functions have exactly the same energy, even though they are independent solutions. So let's have a look at what these things look like. This is a square box, and I'm going to look at the simplest solution, namely nx equals 1, ny equals 1, so the quantum numbers have the lowest allowed values, which is 1 for each. And then we're going to plot what this function looks like. It looks like this. It's simply half a wave in both dimensions, which is just a dome. It's just a dome. At all edges, it's basically 0. Okay? In the middle, it bulges up, and then basically slopes down in every direction. That's the simplest solution I can find. Psi 1, 1. Let's raise the quantum number of ny to 2. So I get now psi 1, 2. X is still quantum number 1, but y has now quantum number 2. And so what I'm seeing along x it's still like a wave like so. Okay, half a wavelength, but along y, there is a full swing of the wave. You see that? That's why it looks like so. So this thing looks a little different than x and y because x and y have different quantum numbers. What about the opposite? What if I take psi 2, 1? Well, now the full swing of the wave happens along x, and along y, here, I only get half a wavelength. Okay, so it looks like so. These two functions here, psi 1, 2 and psi 2, 1, have the same energy. They are degenerate. Okay, they are degenerate wave functions. But they are independent solutions because you can see this is not the same as that, even though they look the same if you look at it from a different angle, because basically the roles of x and y have simply switched. This guy has the same symmetry type as the symmetry of the one above it, in the corner, but they are rotated relative to one another by 90 degrees. So they are not the same. There's a rotation between the two, but their overall symmetry properties are very much alike, and that has everything to do with the fact that they have the same energy. In general, if you have degenerate wave functions, independent solution of the same Hamiltonian, likely to have the same symmetry properties. Okay? That means the wave functions have very similar shapes the way they look, but they're either rotated or flipped or what have you. There's a symmetry relation between those wave functions. Here's the one that is one level up from there, psi 2, 2. Now I have a full wave in both x and y, and I get this wonderful two-dimensional shape. You see that? Very nice. That's what it looks like. And I can go on, and what you will see is the shapes become more and more complex. I get more and more hills and valleys, okay? more and more hills and valleys. But in all these cases, you see that this is all 0 here. The middle part is 0. At the edges of the box, the wave function always slopes down to 0. That's a general thing because it's a requirement I have. It must be so. One more thing about this. If I look at the overall curvature of the wave function, look at the one in the top. That curvature is kind of like shallow. What is a value for curvature? Actually, the second order derivative of a function is defined as its curvature. If I take a second order derivative of that function there, that means that the curvature is not 0, it's something, but it's not a high number. If I go to the lowest one here, this guy, you can see it, has a lot more curvature. If you take the second order derivative of this function, you'll find a higher value. Okay? Now, maybe you remember the Hamiltonian kinetic energy operator has a second order derivative in it. So if the second order derivative of a function is higher, meaning that that function has a higher kinetic energy. I can just look at these functions and say, ah, this guy here, this guy must have higher energy than the one up there. Okay? The more curved the wave function is, the more hills and valleys the wave function has in a small amount of space, the more kinetic energy the particle must have to occupy that wave function. A particle needs more energy to do this than to do that. Does that make sense? All right. So, let's move now our attention to what happens at the edges one more time. Because that's interesting, right? Because we determined that at the edges of the box, the wave function must go to 0. We got very nice solutions in that case. But there's something unsettling about this. Because you can, of course, imagine that an infinitely high potential energy is somewhat unrealistic. Okay? Our goal is to describe an electron in an atom. An atom is not demarcated by a huge potential energy barrier that defines the size of the atom. It's not like that. Okay? Certainly there's a potential energy distribution in space, but it's not a hard edge that suddenly goes from 0 to infinity. That's kind of like dramatic. So we have looked at the situation in this way, and we want to refine that somewhat. So let's first look at this scenario. What I'm looking at here is an in-between situation where I say, on the left there is no potential barrier. On the right there is one. It starts suddenly, but it doesn't go to infinity. It goes to a constant value v. And we have done this before. Okay, we've seen this before. We know that the solutions must look like something like this. On the left, I get these two exponential functions, right? One describes particle to the left, one describes particle going to the right. And so what I'm going to do is, the first function here, that's a particle moving towards the right. And the second one with the r in front of it, that is just a constant, is moving to the left. Why do I put an r in it? Because I don't know what the value is of that number. But I gave it the letter r, because I think it has something to do with reflection. We got a particle here, there's a barrier, bounces back, it moves this way, and we'll call that the reflected particle. So, the particle initially comes this way, and then something happens and it goes this way. In the barrier, I know that the solutions look like that. E, and then negative kappa x. Remember that? It's a decaying exponential. I put a t in front of it because I don't know what the value is going to be. There's some sort of a constant. I call it t because the t stands for transmission. So, how much of the electron is transmitted into the barrier? And how much is reflected off of it? That's what I'd like to figure out. What happens at this barrier? So let's take the wave coming in. Okay, let's assume it comes from the left, travels towards the right, hits the barrier, and then what? Well, since v is not infinite, I can have something like that. In the most general way, most general solution, it will be a decay exponential. It decays with negative kappa. That's the rate at which it decays. So let's take this scenario and let's see if we can solve this for those unknowns, namely R and T. How do I get to R and T? Well, I can say that at this intersection here, at position 0, I need to fulfill the boundary conditions for the wave function. What does that mean? I have two conditions that I need to fulfill. One is that the wave function has to be continuous. Remember that from last time? The wave function has to be continuous. Also, its slope needs to be continuous. Otherwise, its second order derivative doesn't exist. So, at x equals 0, I must have a situation where the wave function on the left and the wave function on the right must meet one another in the same point. Okay? So I can write that in the following way. If I take the wave function on the left and I fill in x equals 0, I simply get 1 plus r. If I take the wave function on the right and I put in x equals 0 in that wave function, I simply get t. Because the complex exponents are all 1 when x equals 0. So I simply get the relation 1 plus r equals t. Okay, pretty good. So I know how t and r are related to one another. What about the slope? The slope at this point also needs to be continuous. So if I take the derivative with respect to x on the left-hand side, okay, I get this times the complex exponent. If I fill in x equals 0 at that point, I get this. I take the derivative of the function above, and then I substitute x equals 0, and I get this number. I'm going to do the same thing on the right-hand side. I'm going to take the derivative of that wave function with respect to x, and then put in x equals 0. And I get this. Negative kappa times t. Okay, so I make sure that this holds, which means that the slope at the position x equals 0 is continuous. You take the derivative of the function, you put x equals 0 in the result, and you do it for both sides. Both sides must be equal, and that's what the relation says. Okay, so I have a relation between t and r from the first condition. I'm going to substitute it in the second condition. Okay, so here on the right hand side I see a t, but I know that t must be 1 plus r. So let's put it in there. Instead of t, I put 1 plus r. That's good, because now I have an equation where the only unknown is r, right? I have an r on the right hand side, I have an r on the left hand side. It's the only unknown, so I can solve for it. Let's do it. Let's write r in terms of these k's and kappas, see what it is. Okay, it's this. You can verify it for yourself. It's not so hard to do. Just solve for r, and r turns out to be this. 1k plus kappa, and then the denominator is I times k minus kappa. That's the denominator. So that's r. What about t? Well, t and r are related, right? So I can just calculate what t is once I know what r is. 1 plus r equals t. And then if you clean up that expression, you can show that t equals this. 2ik minus kappa. The denominator is the same for each, but the numerator is different. Okay, fair enough. We got now an expression for r and an expression for t. What does it mean? Well, let's have a look. The reflection of this particle is dependent on the modulus squared of the pre-coefficient. Okay? So the reflection is proportional to r squared. That's the chance that the electron will be reflected off the interface. Okay, so I basically have to square the expression for r from the previous slide. And if you do that, and you clean up the result, you can show that is k squared plus kappa squared divided by k squared plus kappa squared, which is nothing but uno. That's 1. Okay. Interesting result. Not quite sure what it means yet, but let's have a look. Transmission, those are the same thing. I'm going to take the modulus squared of t, that coefficient, which is the weight of how much is transmitted. And I get 4k squared divided by k squared plus kappa squared. Okay, so let me try to understand my result. And why is it so interesting? So, if a particle comes on this side and travels towards the right, r is 1, meaning there is a 100% chance that that particle will be reflected off the barrier. Okay? Will bounce back. Because r squared equals 1. What happens on the other side? On the other side, I have t squared, which is actually not 0. Okay? That is an actual number. It's a positive number. It's a positive real number. It's a finite chance of seeing the particle on this side. Okay, now I have an issue. Because if there's a 100% chance that the particle is reflected, how on earth can it be on the other side as well? That makes no sense at first sight. How can I think about this? Well, in order to make some sort of analogy, which is a very good one actually, I'm going to look at this experiment. Maybe you've seen this before. I'm going to take a fish tank, and I have a little handheld laser. I'm going to shoot it in from the side. I'm going to tune the angle by which I'm going to couple in, and I'm going to shine it at the interface between the water and the air above it. You know that at some angle, I'm going to have a phenomenon called total internal reflection. This is a perfect high school demonstration in physics class. Okay? The angle has to be right, but if that happens to be the case, then 100% of the light will bounce off the interface. Okay. So what does that have to do with us? Well, if you zoom in on the interface, you will discover something very interesting. Okay? At the interface, so this is basically the situation, that dark line is the interface here. Going to come in from this side, bounce back, but wherever the light hits the interface, you see there's actually some whitish color there, meaning there actually is light energy right there. But it doesn't go anywhere. It doesn't shoot up because it disappears. You see, it's a decaying exponential. It disappears. If you move away farther away, it becomes 0. So if you put a detector here on top, you won't see any light. Light is not reaching it. Why not? Well, because it decays exponentially. What does it mean? There's a word for that. It's called evanescent. It's an evanescent wave. It's a wave that dies out and will never reach my detector. Okay? So if it never reaches my detector, effectively nothing has been transmitted to the other side. This is a so-called non-propagating wave. It's an evanescent wave. Not all waves propagate and carry information from here to there. Some waves die out and will never reach their destination. That's called an evanescent wave. Even though there's an evanescent wave energy on the other side, it's only there when the light is on. When I turn the light off, it's gone. So this whole interface scenario here is simply saying that is solving the Schrödinger equation near the boundaries. That's just what it is. But on the whole, all the energy that happens to be on the other side eventually will come out and 100% will reach the other end. Only light propagates in the reflected direction. None of it propagates in a transmission direction, because in a transmission direction, the wave is evanescent. It's not a propagating wave, it's an evanescent wave. And that's the same with the electron. The electron has a probability of being on the other side, but eventually there's a 100% chance you'll find it on the other side again, on the reflected side. It is only there as an evanescent wave. It's not there as a propagating wave. The propagating wave only happens to be on the left-hand side of the barrier. Okay, so keep that in mind, folks. This is important. This is important because something similar happens to an atom. If I have an atom and I put an electron in there, the boundaries of the atom are not hard boundaries where the potential energy goes up to infinity suddenly. It's not. It's actually something that kind of dies out. It's kind of an evanescent wave that kind of dies out to infinity. So technically you would be able to say, well, the electron has a non-zero chance of being very far away from the atom. And if you say that, it would be right in principle. But you have to understand that that wave is an evanescent wave. Okay? It's an evanescent wave. It means it doesn't carry, it doesn't propagate out. It doesn't go there and transfer information to infinity. So let's move away from this potential energy barrier going to infinity, which required us to say that the wave must go to zero at the beginning of the boundary. That's why that wave goes to zero at the boundary. That's what we required for our kind of simple solutions to the Schrödinger equation. If I lower the boundary, make it finite but constant, this is the situation we just discussed. I get this decaying exponential inside the barrier. It slopes down. In the barrier, it's now an evanescent wave. But I like to not have these sharp edges. I like to have something that is, a gentle function of x. I mean, something like this. This is not even perfect, but this is at least a little bit better. I don't have a hard barrier. I have something that maybe becomes more and more dramatic the farther I move away from this imaginary boundary. Okay, so something that becomes more and more potential energy the farther I move away from it, like here. I would expect something quite similar, but maybe a little bit more, since it's more forgiving now, it doesn't go so sharp. I think that this evanescent part is a little bit more shallow. Okay, that's what I expect. What I want to go to is a situation like this. This is the particle in a one-dimensional box where the potential barriers are sharp, but I want to go to something like this, where they are gentle. In the middle, maybe it's zero, but the farther I move away, the more potential energy there is. So the particle has a harder time to move farther and farther away from the origin. This gets me a little closer to what the atom is. It's not exactly right, but the physics is a little closer to reality. Okay? And so on Friday, we're going to start with this scenario. Okay? A particle in a so-called harmonic well. An harmonic well. The well that defines the harmonic oscillator. All right, see you then.